Um, well, chemists are interested in electrical forces. Uh-huh. You know, nuclear physicists, nuclear chemists are interested in non-electrical forces. One thing that nuclear, if you look at this, there's two protons, two neutrons. What's the charge on that? If you have two protons, two neutrons, the charge is going to be plus two. Nuclear physicists and nuclear chemists, they don't bother with the plus two. Plus for us that's huge. Because if that's plus two and that's the size of the helium nucleus, then that's going to be an extremely powerful oxidizer. Because the size to charge ratio, the charge to size ratio is going to be enormous. Enormous. And so that's what makes an alpha particle so dangerous, because it's a powerful oxidizer. But in nuclear chemistry, they just completely ignore charges. They completely ignore charges because charges, in electrical forces are small compared to the forces that they are concerned with. And the forces that they're concerned with are what? Energy, yes, definitely energy. But what would we call it? Hmm? They're interested in fission and fusion, but they're looking at differences in energy of what? What kinds of energy? What type of energy? Yeah, it's potential energy, but when we think about it, we're looking at potential energy of electrical, like positive and negative for chemists, but they're looking at potential energy in terms of what we call the nuclear force. So, nuclear force, or the strong force. And that's what holds the nucleus together, because electrostatic forces don't. Electrical forces don't hold this together, because if you have two protons crammed into a nucleus, what's holding the two protons together? Certainly not electrical forces. So there's got to be something that is more powerful than electrical forces that holds the nucleus together. Because usually positive and positive repel one another. And that's the nuclear. This is what we call the nuclear binding energy. And so that's what's plotted here in this graph, is the nuclear binding energy. The higher the nuclear binding energy, the stronger the nucleus is. And what they do is they normalize it, because if you have a giant nucleus, then it's got to have a giant nuclear binding energy, but it still might be weakly bound. In fact, that's what happens with the very large nuclei. They become radioactive. And so this is the nuclear binding energy per nucleon. Have you ever heard that word nucleon? What a nucleon is this per proton or per neutron. So they just call them nucleons, protons and neutrons. And so what they do is they normalize this so that we can see how strongly is this nucleus bound per nuclear particle, called a nucleon. And then we can see that some nuclei are very strongly bound. And this just goes to show, in terms of size, smaller nuclei are less stable, larger nuclei are less stable. So something in the middle is most stable. And then also, we could have something in the middle and it's radioactive. We can have something like here around 60. This is the mass number around 60. It's pretty stable. We could have something around 60 and it's very unstable because of the neutron to proton ratio screwed up. If the neutron to proton ratio is screwed up, then it's going to be radioactive. These are the observations in terms of nuclear stability, which we talked about yesterday. One thing that is covered in Chem 1A is something called the mass defect. Do you recall the mass defect? Okay, we should be able to determine the mass. Normally, how are masses of isotopes determined? Yeah, so you add up. You would think you would add up the weight of the neutrons and the protons, and then that will give you the total weight or the total mass.
But then you also have to. I thought you also had to take like the different masses of all the different isotopes and then multiply it by like the frequency.
Okay, that's getting the average mass of the isotopes, but how are the individual isotopes weighed? So, for example, how do you know how much a carbon-13 weighs? I know how much a carbon-12 weighs. Do you know how much a carbon-12 weighs? Everybody should know how much a carbon-12 nuclide weighs. Carbon-12 weighs exactly. It's exactly 12. That's right. Carbon-12 is exactly 12 by definition. That's the definition of the AMU scale, or the atomic mass unit scale. It used to not be carbon-12. Do you know what it used to be? So if you look at an old periodic table, the old periodic tables are going to have different masses, like prior to 1950 or 1940. That's because the standard that they used for the atomic mass unit was different. In the old days, they used to use oxygen-16, and they defined the AMU as one oxygen-16 atom weighs exactly 16 AMU. When they switched it to carbon-12, then it shifted all the masses slightly, and so they just defined it differently. And so how do you know how much a carbon-13 weighs? Yeah, well, and so that comes up to the mass defect. If we take the mass of the neutron, which we know is 1.0087, and the mass of the proton, 1.0073, and add all these up, then the total mass is 4.032 U. I know it's hard to see here, but that's 4.032. Then when you weigh the nucleus itself, it comes out to 4.0015. They don't add up. In other words, some of the mass is missing. 0.0305, 305 U worth of mass is missing. This is called the mass defect. That is, the sum is always less. In other words, the nucleus is always less than the sum of the individual parts. Why is that? Well, why that is this is the mass defect. And the mass defect is we're missing some mass. Mass was not conserved. In nuclear reactions, mass is not conserved. Actually, in chemical reactions, too, mass is not conserved, but the mass changes are so small that they're negligible. In nuclear reactions, the mass changes are much more significant because the amounts of energy that are involved. So you've seen this equation, E equals mc squared. And so what this says is that some of the mass is converted into energy. And so some of the mass of the nucleus, in this case 0.0305 U, was converted into energy to hold the nucleus together, and that's called the nuclear binding energy. And so we can calculate the nuclear binding energy by calculating the mass defect. And the mass defect is not a fixed percentage. It's not a fixed percentage. If it were a fixed percentage, then every single nucleus would have the same binding energy. But what we see is some nuclei are more strongly bonded together, and others are more weakly bonded together. And so the nuclear binding energy is not something that's fixed. It depends on the nucleus itself. And so this is something we can calculate from the data here. Now, how are these weighed? How do you determine the masses of isotopes? You use a mass spectrometer. Do you know what the mass spectrometer is? Pretty much. Do you know pretty much how it operates, mass spectrometer? No? Okay, you shoot individual atoms through a magnetic field, inhomogeneous magnetic field. But first, when you shoot the atoms, you have to charge them. And so you charge them by passing them through an electron gun that shoots electrons, or a particle beam that shoots molecules or atoms at it to create a charge on these atoms that go across. And then you have a charged atom going through a magnet, it gets deflected. And the amount of deflection depends on how much it weighs. If it weighs a lot, then it doesn't get deflected much. There's a lot of inertia. If it's very light, then it gets deflected rapidly. And depending on the deflection, then you can determine the mass using physics. And so mass spectrometer is big. That's how we weigh the individual isotopes. Not only do we get the individual isotopes masses, like neon-20, we can get the mass of that, But we also get its percent natural abundance because in the mass spectrum, you can see the peaks are going to be at different heights. So this is back in, I don't know, chapter 2 or 3 or something like that. And so here, the mass defect is very important. This is how we can tell what the binding energy is. And this is also very important because this tells us, about the energetics. The energetics, we did all this thermodynamics stuff for the chemical reactions. That thermodynamics stuff's so complicated sometimes, with all the equations and trying to figure out, delta G's and delta H's and delta S's. In nuclear chem, the energy calculations are so simple. Do you know how you can determine how much energy is gained or lost in a nuclear reaction? It's very simple because mass is not conserved in nuclear reactions. What's mass and energy are conserved. And so all you do is weigh the reactants using like a mass spectrometer or something, and then you weigh the products. And then you see what the mass difference is. If the mass went down, that's exothermic. And that delta M, which we'll put in here, delta M, and then C is the speed of light, and then we'll get the energy of that here in joules. And so we could figure out, if mass was lost, it's exothermic, and we can figure out how much energy is released by using this equation. Delta E is equal to delta MC squared. If energy is gained in that reaction, then it's endothermic, and we're getting to something less stable, and we can calculate the amount of energy. So it's a very simple calculation. All we have to do is convert from AMU to grams. Do you know the conversion from AMU to grams? The conversion is pretty easy to remember how to derive. So I might as well talk about that right now. The conversion is, we know that there's exactly 12 U in one carbon-12 nuclide, or atom. And then we know that there is 6.022 times 10 to the 23rd carbon-12 nuclides in a mole of carbon-12 nuclides. And then we know that there's exactly 12 grams of carbon-12 in a mole. And so when we look at this, it's easy. It's super easy to remember, except in books they don't. They make it hard to remember. If you go to a book, it's like 1.6 times 10 to the minus 32 kilograms per AMU or something like that. But if you remember it this way, it's much easier because the 12 cancels. The carbon-12 nuclides cancel. The moles of carbon cancel. And so what this gives us is there's 6.022 times 10 to the 23rd U per gram. And so when we use this equation here, we need the mass. The mass has to be in kilograms. And so delta E is equal to delta MC squared. Delta M has to be in kilograms. So we'll go from delta U, the difference in atomic mass units, to the difference in grams, to the difference in kilograms. So we'll just convert that. C is C, 2.998 times 10 to the 8 meters per second. So what this gives us is, it gives us units of kilograms meters squared per second squared. Do you know what a kilogram meter squared per second squared is? Kilogram meter squared per second squared. That's defined as 1 kilogram meter squared per second squared is the definition of this is from thermodynamics part 1. Joule. That's the definition of a joule. And so 1 joule is defined as that. And so this is going to give us our delta E in joules here, the nuclear binding energy in joules. But physicists don't like joules. Physicists like electron volts. So we probably convert it into electron volts after that. And the conversion's pretty simple for electron volts. This is essentially, well, anyway. So calculating energetics of nuclear reaction like this, if we were to bring these together. But we have other types of nuclear reactions, and that's what we're going to look at briefly today. So when something's radioactive, what's going to happen? Well, if something's radioactive, let's say it's way too big, what can happen is it can break apart into smaller pieces, or if it's very small, it can fuse together into larger nuclei. And so we have fusion here for smaller, that is favorable, and fission for larger, that's favorable. And so we go in terms of energetics here. So here we have the fission. This is a multi-step process. And so we have a neutron come in here, and that's going to activate this. In the process, it makes some smaller particles, U-236. I don't know what that is. 3 neutrons. So fission fragments plus neutrons. Eventually, this is going to decay all the way to lead. And so we can calculate the mass changes, and then we can calculate how much energy. And the quantity of energies here are large compared to chemical reactions. And one of the homework problems they go through, like, for example, compared to dynamite, the chemical potential energy of dynamite is very high. It's very explosive. But for nuclear reactions, dynamite is very small quantities of energy. Well, what can you do with this energy? What you can do with this energy is you can use that to boil water. And if you boil water, that is here. And are you guys familiar with a nuclear reactor like this? All right, then you have the confinement shell, and then you have different water systems. The first water system comes into direct contact with the fuel. And the fuel is put into these fuel rods, and these fuel rods are going to contain pellets of this stuff. But it's a lot of energy. So whatever you use is going to start getting hot, and as it gets hot, there's a potential for melting. These are like zirconium rods, I think, and so there's potential for melting the zirconium. And if it melts, then all the fuel is going to melt, and it's going to just be a puddle of molten fuel down here. And so you have to control the temperature. Well, one way you control the temperature is you submerge it underwater, because water has very high heat capacity and it can absorb a lot of energy. And so as long as the water, the cooling water is there, then it's not going to get too hot. The other way you can prevent it from getting too hot is you have control rods. These control rods can be lifted in and out of this. And what needs to happen to get fission going is it needs to absorb a neutron from some source, maybe from some other radioactive nuclide, like here. It shoots off 3 neutrons. And so it starts the process. And so what the control rods, they contain, like, I think, boron. And what they do is they absorb neutrons. So you have a neutron absorber. And so what you can do is if you want the reaction to go quickly, you lift the control rods out from the fuel rods. If you want to slow it down, you put the control rods back in. That absorbs the neutrons, slows down the fission. So as long as that stays cool, then it's no problem. No problem. And then what happens is you have this internal, then there's a heat exchanger here. And the heat exchanger is going to go to a secondary water system here. And the secondary water system is designed so that it boils the water here, creates steam, and then drives a steam engine here, or steam turbine, which generates electricity. This isn't very efficient. The efficiency of this is pretty low, converting heat into electricity here. And we're generating heat. It's not very efficient, but the quantity of energy that's released from nuclear is huge. So even though it's not very efficient, it can generate a lot of electricity. And so you have this secondary system here, and then we just recycle water, it condenses there. And this water is highly radioactive, the primary. And then the secondary, there could be some here. And then in order to condense the steam, there's tertiary water. And this tertiary water just comes from the river here or the ocean or a lake. And so they just pump water in here to condense the steam back into water so it can be boiled again over here and generate more electricity. There's no way to store the electricity unless you have some batteries. So this is just done on demand. So when there's a high demand for electricity, they lift the control rods out. When there's low demand, they'll put the control rods in here because you can't store it. And so people are looking at how to store electricity because that way you can generate it continuously rather than wait for peak demand. All right, so this is fine as long as as long as the pump keeps working. I guess Fukushima, they had pumps and they had backup pump. I think you would think they'd have multiple backup systems in case there was a pump failure, but they only had one backup pump, from my understanding. And that backup pump was swamped by the tsunami, and so it wasn't running. So the water wasn't circulating. If the water wasn't circulating, it's going to superheat it and boil. And therefore, it's no longer going to be cooled or quenched by the water. And when that happens, then, of course, the fuel can get too hot. And if the fuel gets too hot, and then the control rods aren't there, then the reaction can start to take off. And you can have something called a meltdown. And the meltdown is you just get molten fuel there. But, there are different levels. When the metal gets hot and there's water around, then what can happen is the water can get reduced into hydrogen gas. And so what happened here is hot metal coming into contact with steam created hydrogen gas and filled the confinement shell with hydrogen gas, resulting in a huge explosion. But not all the explosions were the same. There's a guy in Vermont who used to be a nuclear engineer working at one of the plants. I forgot which one, but he turned into a consultant, windward consultant, I think. But he was analyzing some of the explosions. And one of the explosions there at Fukushima, or maybe two of them, were kind of different than the others. You have the normal hydrogen explosion, but then one of them looked like a big mushroom cloud, and it had quite a bit different force. And that was a subcritical. He was saying that was like a subcritical nuclear explosion. And that is, the reaction got so fast and so violent. What happens here is this. This sets off a chain reaction, and explosions happen when too much energy is released in too short of a time. And what we have is exponential growth of neutrons, because these 3 neutrons will create a total of 9 neutrons, and those 9 neutrons will create a total of 27 neutrons, and so on and so on. And so pretty soon this is going to skyrocket. When this skyrockets, then you have the potential for a nuclear explosion. But nuclear explosion, they say you need a critical mass of uranium. A critical mass of uranium is about the size of a grapefruit. And so if you have something like that, then you're going to have a nuclear explosion. And therefore, they never have that much uranium in a reactor like this because they don't want this to turn into a nuclear bomb. But, even with subcritical masses, you can have small events. And it wouldn't be the first time that kind of event happened. That kind of event happened in Texas, where they had like a subcritical explosion, which was nuclear. But anyway, going back to this, of course there are problems with spent fuel. What do you do with this? Because it stays radioactive for a very long time. And so that's usually stored. like at San Onofre, they have a huge amount of spent fuel stored there. And that's, okay, so people are looking at what to do with that. And that's one of the challenges of this. Otherwise, it's pretty efficient way of generating electricity. Not everything has a very long half-life. Some things are very short. Tritium is very short. What's tritium? Okay. A is a year. 12.33 years. Carbon-14, 5,715 years. Which one's short? Cesium, 30.2 years. Bromine, 17.6 minutes. Phosphorus, 32. This one's pretty familiar because all the biochemists work with phosphorus 32. So I on my floor shared the floor with biochemists group, and they're always putting P32 in there so that they could follow reactions and biochemical reactions, see where the radioactive atom ends up. But these are the long ones here. Uranium-238, 10 to the 9th years. Plutonium, actually plutonium's not in here, in the same order of magnitude. Radon, radon is a worry around here because radon is found in emanating from some granitic rocks. It's a gas and it's an alpha emitter. So if you inhale radon, it emits an alpha particle, and that alpha particle is a strong oxidizer. So if you inhale it, that strong oxidizer can damage your lungs, whatnot. But that has a 3.8-day half-life. All these are first order. And so we could use first order kinetics and analyzing. So this is the first order integrated rate law. ln A at time t over A at time 0. This is just the number of nuclides at time t, and the number of nuclides at time 0 is equal to minus kt. And so we could use these for radiocarbon dating, for example. Carbon-14 is formed by a constant rate by bombardment of nitrogen with neutrons coming from space. So we can do that. And living objects are not incorporating new carbon. So you can figure out when something died or stopped collecting. And so this is the first order decay curve. We have other types of dating too. As this only dates thousands of years, but something like potassium with a half-life of 1 billion years can date older objects. And potassium-40 would decay into argon-40 and calcium-40. So you can figure out the ratio of daughter to parent. Daughter would be the products, parent would be the reactant. Not going to do any calculation. The other type of reaction is fusion. Is here we're fusing smaller atoms, smaller nuclei into bigger ones. And if we take the mass of this and the mass of this, there's a difference. And in this case, the mass of the products will be less. Then we can calculate the energy using delta E is equal to delta MC squared. And the energy is huge for fusion. And so this is very promising. And the other thing that's very promising is, although tritium is radioactive, helium's not. Helium's very stable, so it's a stable product here in its form. And so fusion reactors, the problem with those is you need extremely high energies to fuse nuclei together. What you have to do is you have to have a high energy collision because the nuclei don't want to fuse together. Nuclei are going to be repelled by electrical forces because each nuclei is positively charged. So you're trying to force the positively charged, so they're going to repel one another. So you have to force them with huge amounts of energy. And so how do you get these huge amounts of energy? Well, one is you could use like an accelerator, particle accelerator. They have linear accelerators where they shoot the particles on a head-on collision course. And when they collide together, they might fuse. But that's one particle and one particle. And then you have cyclotrons. You know, these cyclotrons, you start spinning these faster and faster, and then you put something in target, and boom, you get a big collision. And then you might be able to fuse the nuclei together. And so that's how they can generate things like this, like oxygen 17. They can take a nitrogen and accelerate it towards a helium and get the two nuclei to fuse together to make an oxygen 17 and a hydrogen. Or a phosphorus 30 here by taking aluminum and helium and shooting those together extremely high speed so that the nuclei fuse together. This P30 can decompose into silicon here. Or here, uranium. This is fission here, though, but uranium takes on a neutron. For neutrons, you don't need high energy. For neutrons, you could use room temperature neutrons. The reason is neutrons have no problem fusing with the nucleus because there's no electrical repulsion. So a room temperature neutron can easily bind to a nucleus. This is why neutrons are so dangerous. Neutrons are very dangerous because what they can do is they can easily react with the nuclei and cause those atoms to become radioactive, because it screws up the neutron to proton balance. So, at one time back, I think in the 80s or something like that, they were talking about making a neutron bomb. Have you ever heard of a neutron bomb? They're talking about a neutron bomb because the idea behind the neutron bomb was that if you detonate a neutron bomb, a whole bunch of neutrons get generated, and those neutrons will bind to the nucleus of people and animals and whatever else, and then it'll destabilize the nuclei, making them radioactive, and then people will die eventually. But it leaves all the buildings intact because all you need are thermal neutrons. You don't need high energy neutrons, right? But the problem is the thinking is, yeah, okay, the people and life are going to die, but the buildings are all going to be radioactive because all the nuclei in the buildings are going to absorb those neutrons as well, and those atoms will become radioactive, and you can't go in there and occupy that. So I don't know whatever became of the neutron bomb, but that was an idea that somebody had. So they're getting better with this. To generate these high energies, they use a plasma, which is like the sun. The sun is the thermal plasma. So they try to generate plasma, but if you have a plasma like the sun, it'll melt everything. And so what they do is they confine it using magnetic and electric fields. And so they combine it in the vacuum, so it can't get anything hot. If this is a vacuum, it doesn't transmit heat. And so, but it's, the amount of energy that's consumed in creating a huge vacuum and then creating this high energy plasma is huge. And so it used to be negative. It costs more energy to generate fusion than you got out, but it's changing. People are getting close to having it come out on the positive. In fact, I think I saw a paper recently, not too long ago, where they said that they're getting net generation of electricity, or not electricity, but energy. And so that's promising. So more research is being done on that. Here's a linear accelerator to cause the atoms to fuse together. Here's a cyclotron. And you can accelerate and cause high energy collisions. they have a huge one in Europe of the Large Hadron Collider. Um, they can generate enormous energy. They can have massive collisions. And they're looking for new insights into the nature of matter. But let's take a look at some other nuclear reactions. What happens if the proton and neutron ratio get all screwed up? If the proton and neutron ratio get all screwed up, then we can have things like beta particles be generated. Beta particles, again, convert neutrons into protons. And then this beta particle, an electron, originates from the nucleus. That's one thing. And so this will increase the number of protons, decrease the number of neutrons. Positron, which will decrease the number of protons, increase the number of neutrons by emitting a positive electron. Here's an example of those. Electron capture, which will create will consume one proton and generate an extra neutron, or not. So we still end up net 202 to 202, followed by X-rays. Alpha particles, this is one is too big, and so part of the nucleus splits off. Then we have gamma radiation. Gamma radiation is not going to change. Gamma radiation and X radiation are just what happens when these reactions can be highly exothermic, and so when they're highly exothermic, they can emit high energy, like gamma rays and X-rays. We can detect those using Geiger counter, which we talked about last time. Except Geiger counter, the problem with Geiger counters can't measure alpha radiation. They can't measure alpha radiation because the Michael window here, in the case of this, will block alpha particles. Alpha particles, to shield yourself, you only need a piece of paper, basically. But beta and gamma ray radiation you can detect with a Geiger counter. So when we look at radiation, there are different units of radiation. You don't have to memorize these. There's a unit just based on decay. You know, how fast is it decaying? Are there 10 atoms per second, or how many nuclei are decaying per second? And the number is usually huge. So the units are per second, and it's disintegrations per second. So the amount of radioactive material decaying at the same rate as 1 gram of radium. 1 gram of radium decays at a rate of 3.70 times 10 to the 10 disintegrations per second. We call that 1 curie of radiation. So if it's decaying at this 37 billion disintegrations a second, then it's 1 curie's worth of radiation. But you could have 1 curie's worth of radiation, but it depends on what type of radiation you're talking about. You know, is that radiation gamma radiation, alpha particles? What is it? And so one of the things to understand, well, they're going to have different energies. You know, gamma rays aren't the same as X-rays. And so we have something called the rad. The rad is the absorbed dose, radiation absorbed dose. And so the units of this are gray. 1 gray radiation deposits 1 joule of energy per kilogram of matter. And so 1 joule of energy per kilogram of matter, well, it depends, you know. It depends on, we can get 1 joule of visible light per kilogram of matter. And would you worry about visible light? Not at all. But if you had 1 joule of gamma rays, and so this is the same. 1 rad of gamma rays is not the same thing as 1 rad of red light. Now, 1 rad of red light you wouldn't worry about at all if red light's being emitted by the radioactive source. So this isn't as useful for us. This is the most useful, which would be the REM, which is the equivalent dose. The REM is measured in sieverts. 1 sievert is 100 rem. 100 rem is 1 rad of radiation times Q. Q is the quality factor. And so if it's X-rays, the 1 gram of X-rays and gamma rays and beta particles are about the same, although X-rays, gamma rays are quite a bit different in terms of energy for us. But those are grouped together. However, if you're exposed to neutrons, then we'd have to multiply by 3. You know, the number of Curies we'd multiply by 3, or the number of rad we multiply by 3. And that's for slow neutrons. Slow neutrons would be room temperature neutrons, neutrons that haven't been accelerated. They're just moving like the gas. However, we'd have to multiply by 10 for protons and fast neutrons. So, you know, if you get protons and fast neutrons are much more hazardous than slow neutrons, which are much more hazardous than X-rays and gamma rays, beta particles. But look at what's worse. The worst is alpha particles. Alpha particles, because these are highly ionizing. You know, strong oxidizers are going to ionize things. All these are ionizing. The neutrons, though, can cause damage, other types of damage. And so the SI units are shown in blue. Sources of radiation are relatively harmless when external to the body, and extremely hazardous when taken internally, as in the lungs or stomach. The reason it's relatively harmless, do you know why, the external parts of your body?
Keratin, which is like dead skin cells.
Yeah, that could probably absorb some of the radiation. The other reason is we're exposed to radiation every day. Ultraviolet radiation breaks bonds, like the carbon-carbon bonds in DNA. And so when I was taking biochemistry, which was decades ago, I remember this number. The DNA, you know how many times the DNA got cleaved per day? This is back when there's more ozone. This is back when you didn't have to wear sunscreen all the time. But maybe I should have worn sunscreen more frequently. But anyway, it was like 200 times a day your DNA gets cleaved by ultraviolet radiation. But, you know, I guess we've evolved to take care of that because they're repair enzymes. So these enzymes go back up and stitch things. And then there's a correction. They check for errors in the DNA. And so there are enzymes that take care of that for skin cells and that type of stuff that's exposed to the sun's radiation or radiation from space. Because not only are we bombarded by ultraviolet, we're also bombarded by cosmic radiation continuously, and it causes damage. But the problem is if you take it internally. So if you inhale, let's say you inhale alpha particles are gas, then that's going to cause damage to your lungs or stomach. But here you don't have repair enzymes, the same repair enzymes in your lung tissue. So if there's cleavage of the DNA in your lung tissues, it's not going to be repaired. It's going to lead to potentially mutations or whatnot, cancer. Okay, other forms of radiation, X-rays, gamma rays, because they are highly penetrating, are hazardous even when external to the body. And so X-rays and gamma rays are highly penetrating. They're highly penetrating, that's why you need lead. Lead has lots of electrons and will absorb it. But gamma rays are extremely penetrating, and they can cause damage. All right, so that's like a brief survey. I mean, we might have some general questions on the final. And,
What was the atomic bomb? Was it fission or fusion, and what did it give off?
there are two types of atomic bombs. You know, the original one is fission, and then they have fusion bombs as well. And yeah, give off. There were a whole bunch of nuclear tests, like in Nevada and elsewhere in the South Pacific. A whole bunch of nuclear tests. So there's radioactive isotopes, just natural background radioactive isotopes from those tests also.
And did they use
uranium, and plutonium for those. Plutonium. They're talking, because there's some plutonium. It depends on what type of reactor you have. There are certain types of nuclear reactors called breeder reactors that generate plutonium. And in Fukushima, there's some plutonium generated, but did I tell you? Some of the stuff you read is very interesting because some people were saying, oh, plutonium is so heavy. It's so heavy, we don't have to worry about it dispersing into the environment because it's so heavy. But if you think about how heavy is a single atom? Not heavy. How heavy is a tiny cluster of atoms? How much does that really weigh? It doesn't weigh anything. In fact, they were doing studies, when there's a big dust storm in China, they can measure increases in the mercury levels across the U.S. and they can measure if it's blowing from the let's say the west to the east. They'll detect elevated mercury levels as far away as New York, from dust storms in China. And mercury is very heavy. And so the argument that, plutonium's heavy, we don't have to worry about it dispersing into the environment seems faulty. But people were claiming that and other stuff. So, but it's good to have good scientific debate so that these things can be hashed out. But Chernobyl was different. Chernobyl was a graphite reactor. And so a totally different construction than Chernobyl. But that was another. 3 Mile Island was more like Fukushima style, but they just had a meltdown there. But those are some of the risks. The benefits, though, are it's relatively clean. I mean, it's not generating greenhouse gases. Like a lot of electricity is generated by methane combustion, and so in that respect, it's not. Although methane, if you're going to combust something, methane would be good to combust compared to coal. Coal combustion is a lot dirtier than methane. Methane burns pretty cleanly. I mean, we burn methane in here all the time with a Bunsen burner, and we don't really worry. There's a little bit of worry about carbon monoxide, but little else. Well, we have to think about generating electricity if we're headed towards that, away from. And so if it's electricity, there's some countries that rely totally on nuclear. I think like Japan's one of them. And France is heavily nuclear, but I think the technology has improved dramatically. And then there's talk of mini nuclear reactors and using thorium. And so there's been a lot of development in nuclear power plant design. And so they can make a lot safer nuclear power plants. I think when the Fukushima was undergoing their meltdown there, the U.S. offered, to give them some special coolant, and I was thinking, what is the special coolant? It's some top secret military coolant that they use on nuclear submarines in case, there's some problem with the cooling system. They don't want any kind of meltdown on a nuclear sub, so they have some special coolant. And so I was thinking it must be something that, that has a very high heat capacity that can absorb a lot of energy and cool things down. So I thought and they were going to fly that out right away. And so I was surprised when, the Japanese government refused. As they refused that help, I thought, wow, why would you refuse that help? And then I realized why they refused the help. They refused the help because it was already too late. It already melted down, but they were keeping it secret at that time. So now it makes sense, But there could be more nuclear in the future. I heard, I don't know if this is true, but I heard they're going to reboot one of these old nuclear power plants in California. I don't know. San Onofre, actually my friend, well, not a close friend, but a friend of mine who's an engineer, just got a job at San Onofre as a safety engineer there. And so he was extremely excited about this new job at the San Onofre nuclear power plant, about to start, with really good salary. He didn't mind working at a nuclear power plant. And then they shut it down. They shut it down because of the fuel rods. Did you hear about the fuel rods? Fuel rods started to crack. It was a defective fuel rods. They couldn't repair it or something. This is zirconium fuel rods that they have. If you go to this Windward, I think it's called Windward or something, he has a lot of videos. You know, he has actually some fuel rods, and then he has some pellets that look like fuel pellets. So if you want to see what these look like, and then he treated this because he was showing what happened. You know, when these fuel rods get hot, and then you spray steam on them, and then you generate hydrogen gas, and then he ignited the hydrogen gas that formed. And so he did an actual demo. It's a pretty interesting demo. I'd show. But when I was a student, I was working with a lot of ceramics. And so one of the things, you know, have you ever heard of Hanford? Hanford is a place near Spokane, Washington, I think. And they have a huge lake that's filled with radioactive waste. And this radioactive waste they're worried it's seeping into the groundwater, contaminating other parts of the environment. So people are thinking, well, what should you do about Hanford? If you put them in the steel drums, you know, the steel drums are eventually they don't last forever. The steel drums so they were looking for a more permanent solution. So this was interesting to me because I was working with glasses at the time. And so what they wanted to do is they wanted to put chemicals into the lake, and these chemicals would react to form a glass tomb. And so they wanted to form a glass tomb, and if you can encase all the radioactive nuclides into the glass, then it's not going to leach out of the glass into the groundwater. And so I have are you interested in seeing a glass bead that I have from that? I'll bring it in. Yeah. I have one, but I don't know if it ever went commercial. But this is from a talk I attended. I'll bring it in. But what we'll do next is we'll have a review now. So let me stop this or pause this.